talk about fuels and fuel systems, and the first thing we want to talk about is the characteristics of aviation gasoline. And aviation gasoline has the characteristics of having a high heat value, a lot of energy in it, and also having high volatility. High volatility is a characteristic, but what do we mean by volatility? Well, what volatility is a measure of the tendency of a liquid substance to vaporize under given conditions. And you do want aviation fuel in an airplane to vaporize under the right conditions. But a fuel that vaporizes too readily can cause vapor lock. You can get vapor lock in the fuel lines and in the engine if the fuel vaporizes too easily. On the other hand, a fuel that does not vaporize easily enough can cause hard starting, and you don't want that either. So you want it to vaporize under just the right conditions. Now, when you have fuel vaporization, it always is accompanied with an absorption of heat. An absorption of heat always must accompany the process of fuel vaporization, and that, by the way, can contribute to carburetor icing problems. Now, let's talk about the additives that we put into aviation fuel. In aviation gasoline, we add tetraethyl lead, or rather, the factory does when they manufacture the fuel. And the purpose of adding tetraethyl lead to aviation gasoline is to improve the gasoline's performance in the engine. And we're going to talk more about that in a little bit. When we put tetraethyl lead in, we have to put something else in the gasoline to get rid of it, and that something else is ethylene dibromide. Ethylene dibromide is added to all the grades of aviation gasoline, and the purpose of adding it is to scavenge the lead out of the engine, to scavenge the lead oxide from the cylinder combustion chambers. Now, the purpose of putting that tetraethyl lead in is to help control detonation. And what is detonation? Detonation is an abnormal type of combustion. What happens is the first part of the charge burns in a normal manner in the cylinder, but the last part of the charge explodes. It burns almost instantaneously, and it basically slams down on the head of the piston just like an explosion. The characteristics you're going to get in the cylinder when detonation is taking place are a rapid rise in cylinder pressure, excessive cylinder head temperatures, and a decrease in engine power. You're going to lose power in the engine because there is damage taking place in the cylinders in the engine because of the rapid rise in cylinder pressure and the excessively high cylinder head temperature. So you don't want it to happen, and that's why tetraethyl lead is added to the fuel. Now, the anti-knock qualities of aviation fuel are designated by grades: 100 octane, 80 octane, and so on. The higher the grade is, the more compression the fuel charge is capable of standing without detonating. And there are two different scales that are used to designate fuel grades. Fuels below grade 100 are classified by octane numbers. So at and below grade 100, we actually call it octane numbers. But if they have greater anti-knock qualities than 100 octane, they're classified by performance numbers. And let's talk for just a second about what we mean by the difference on these. Basically, when the fuel scales were originally developed, everything was based on a mix of isotane and heptane. And if you had 100% isotane, you would have 100 octane fuel, and you'd have fuel with equivalent anti-knock properties of 100% isotane. The problem is that we became able, through additives, to get fuels with better anti-knock qualities than 100% isotane would give. And so you can't have 100 octane anymore because you've got fuel that is better than 100% isotane. So they call them performance numbers instead of octane, but it means really essentially the same thing. It's how the fuel is going to behave in terms of anti-knock qualities, and common terminology is that they're both called octane, even though technically technically, only fuels with grades at and below 100 have octane numbers, and technically, fuels with grades above 100 have performance numbers. Now, when you have a fuel rating, let's assume you've got a rating like 100, 130 octane or grade fuel. They want to know for the test what the second number in that fuel rating is indicating. And it is the rich mixture anti-knock rating for the second number in that fuel rating. The first number, by the way, you might want to know is the lean mixture anti-knock rating, although they do not ask you that on the written exam. Now, aviation gasolines are color-coded, and they're color-coded for the purpose of identification. For example, grade 100 low-lead aviation gasoline is blue, and you can see the blue color there. There is a blue dye in it so that you can tell by looking at the color of it what grade of fuel you've got. Grade 100 low-lead aviation gasoline is blue. Now, as far as turbine fuels are concerned, for use in a turbine engine, both kerosene and gasoline each have certain advantages. But kerosene has a higher heat energy per unit volume than gasoline does, and that's because kerosene weighs more per gallon. So kerosene is the fuel of choice for turbine engines. It has a higher heat energy per unit volume than gasoline does. Now, jet fuel identifiers work differently than the octane numbers for gasoline does. Jet A, typically used in civilian aircraft. Sometimes you see trucks around that are labeled JP4 for Jet 4. Those letters and numbers are simply identifiers. They're type numbers, and they have no relationship whatsoever to the fuel's performance in an aircraft engine. So whether the fuel is called JP1, JP4, Jet A, Jet B, has nothing whatsoever to do with the performance of the fuel. It's simply a way of identifying it, and in that way, jet fuel is different than aviation gasoline is. Now, jet fuel is more susceptible to contamination than aviation gasoline is. And the reason for that is because jet fuel is higher viscosity. And the higher viscosity of that jet fuel holds the contaminants in suspension better, and that makes it more susceptible to contamination than aviation gasoline is. Now, let's assume that you've got a piston engine aircraft and it gets misfueled. Somebody accidentally puts jet fuel in so that the aviation gasoline in the tanks is contaminated, and it's contaminated with jet fuel. What do you do about that? You have to drain the fuel tanks and start all over again with a proper octane rated fuel. A piston engine aircraft cannot operate on jet fuel. The engines are simply going to quit. So if you get those tanks contaminated with jet fuel in any proportion, what you have to do is drain the fuel tanks and start over again, refill the tanks with a proper octane rated fuel. Now, on the other hand, let's assume you've got a jet aircraft that is misfueled, and they put aviation gasoline in with the jet fuel. That is not near the problem, because aviation gasoline can be burned by a jet engine when it's mixed in with jet fuel. The problem with doing that is that the tetraethyl lead that we talked about in the aviation gasoline is going to form deposits on the turbine blades when it burns, and that's not real good for the engine. So in general, you don't like to do it, and in a lot of aircraft it has to be logged how many gallons, and there's a limitation on how many between overhauls of aviation gasoline that you can use, but it can be, if it is mixed with jet fuel, it can be burned by a jet engine, but you should expect the lead to form deposits on the turbine blades in that turbine engine.